So this will also be a really great example of walking through a whole statistical downscaling process when in particular you're presented with the challenge that you have a stakeholder for whatever reason cannot use all the available global models. And we'll get into that in a minute. So that is actually the first part of this, is just how do you pick which GCMs to work with in the simulation. The other thing, of course, is the downscaling approach itself, and as Paul mentioned, there will be equations involved in this, but we'll get to that. And then finally itself, the projections we have thus far for the Edwards Aquifer region and some next steps that we are pursuing. So I do want to say up front a note of thanks to OU's Supercomputing Center for Education and Research, specifically Henry Neiman and David Atkins, who helped with the supercomputing side of things to make sure all of this would work to produce projections for the Edwards Aquifer. So, first things first. Oftentimes in the literature, and it's in part to address the uncertainty question that was raised, is it's often recommended to use all the global climate models, but it is also at the same time often very unfeasible for different applications, whether it be for computing capacity or lack of expertise or any number of different reasons. It becomes an unfeasible thing to do. Like I said, with CMIP6, there's 100 models. That's kind of hard for a lot of our different stakeholders to use. And that was also the case in this, in talking with Hakan and with Devadatia and with Ali Murchie, who is also from Oklahoma State University, working on this project. So our challenge is to select a few global models that meet some very specific criteria. First off, it doesn't matter if it's a GCM if it doesn't have variables you want to downscale to begin with, so that's a kind of hard limitation. And in addendum for this, also you want it to be run for the emission scenarios that you want to work with too. We also want things that are going to capture the historical skill for the climatology of our variables of interest, as well as trying to represent the future spread of the ensemble. We don't want to ignore the uncertainty and just pick those things that are skillful. The reason for that is we have found in the past that there are a lot of models that cluster together because we are humans and we share code. There are different modeling components from different modeling centers that are in common, and so they tend to cluster together, and that can make things a little overconfident. So we actually want a subset of the GCM ensemble, or the whole collection of model output, to be capturing that future spread. So in this case, what we decided to do was to work with the Edwards Aquifer region with 5 models per ensemble, CMIP 5 and CMIP 6, CMIP being the coupled model intercomparison project phases 5 and 6 respectively, which are sort of nomenclature for the GCM, for the generation of the global climate models we are on. So interesting and fun note of history, when they went to do the 4th assessment report, they were still using CMIP 3. So, but that is because they finally decided after the 4th assessment report to put the GCMs on the same name generation with the assessment report title. So it's a fun bit of history there. We had an interesting disconnect. Ooh. Technical difficulty, excuse me. So for our purposes here with the global models, because they are designed more for larger scale patterns, we also want to evaluate them on that same scale, not necessarily in the Edwards Aquifer region's itty-bitty region by comparison of South Central Texas. So our focus in the evaluation was actually on the Southern Great Plains region. And this is the same region used for evaluation and a lot of analysis for the National Climate Assessment. So this is actually the regions for the National Climate Assessment analyses. So I'm going to summarize the steps first and then go through some specific important components and the results from that. So step 1 here is for a given variable. What we calculate is from that ensemble, let's say we have 30 models for this example, we calculate every single combination of 5, the mean of those. So you have however many thousands of combinations here and the mean of those particular 5 models for each combination for a given variable. So you can repeat with different variables. From that, we can calculate the normalized root mean square error for all the combinations of those model means, and we normalize for a reason. The other thing that we look at, so that normalized RBC, I should say, is essentially historical scale. I was about to say future scale. Boy, that would have been interesting. But for historical scale. Then there is a metric called fractional range coverage, which is then also done with each combination of 5 using the projected changes from those global models. And we'll get into what fractional range coverage is in a moment. Based on that, we can actually calculate the Euclidean distance using the root mean square, the normalized RMSE, and the FRC for each combination from an ideal point. And as we'll get to that for a second here, you repeat all of that for each variable of interest, and then you can combine them to create a multivariate distance from which you select the optimum subset to work with. Which I kind of said the next thing, but where that comes in is a simple visualization here, where each of these dots in blue are perhaps one possible combination of 5 that we might work with. Ideal up here is this 0.01, where you have 0 error, but you also represent the full spread of the ensemble. So essentially what we're picking with this approach is the combination of 5 models that has the shortest distance to that particular point for the collection of 3 variables. The fractional range coverage is pretty well established. It essentially is the percentage of the range of the full ensemble that's covered by a subset. And it's a fairly simple calculation that's been used in a number of studies. For each 5-member subset, we basically look what's the maximum, what's the minimum, and that is over the same range in there. That goes from 0 to 1. It is bounded from 0 to 1, so a value of 1, of course, would mean fully captured the spread of the full ensemble in whatever subset you are working with. Following along with other literature, as it's been done with them, this metric is calculated every single grid point, and then it's averaged over our domain of interest with the subgrid planes to give us the final value for that particular metric for every single subset combination. The goal here for us is to maximize the fractional range coverage and minimize the error, essentially. So we're basically looking for the minimum Euclidean distance between the subsets and 0.01. 0 being the minimum possible error, 1 being the maximum possible FRC value. So it becomes a very simple thing for each possible combination that we have to calculate that sort of Euclidean distance. Of course, we have to do that Euclidean distance calculation for each variable independently. And so we have run into problems, of course, how do you combine information from multiple variables, right? Fortunately, a similar situation was run into by Ben Sanderson in 2017, and he proposed actually a fairly simple and very effective linear combination approach to combine sort of similar things from a multivariate weighting scheme approach that he was devising. So we employed the same scheme here to actually combine those Euclidean distance values for every variable to get a final multivariate Euclidean distance for every ensemble subset that we could possibly use. So we get the multivariate distance this way for each possible subset combination. And that is effectively what this is like. It reduces to this in a linear combination because it's equal weighting for every variable where you have that Euclidean distance for high temperature, low temperature, and precipitation combined together in a multivariate distance for each ensemble subset that is possible. And from that, basically looking for which subset has the smallest value here, effectively, to choose which models that we work with. So, that in mind, this is actually the group of models that were originally picked from each of the 2 ensembles, CMIP5 and CMIP6. I'm not going to read all of the models there, I'll just leave that up there for a minute for you. But they do a good job together of capturing historical climatology, as well as capturing the spread of the much larger ensemble in here. And that was the point. Again, we don't want to necessarily ignore the uncertainty. We want to incorporate the uncertainty into what we're doing here in applications of decision making. So, first pretty map of the day. Let's see. So, what this particular image shows, and there's a few of these, so let me walk through it a little bit here, is essentially the error of the full ensemble, all 30-odd models in this case, versus the error of the subset mean for precipitation in this case, and this is CMIP5 on the left-hand side. This is all for CMIP6 on the right-hand side. And yes, there's going to be error in there for sure, But I want to make a point to note that this is actually fairly reduced from the error of the full ensemble in both cases, actually, which is great for us, considering this was also a multivariate approach. It was not necessarily tuned to one specific variable over another. One can say likewise for temperature. This is the high temperature ones in this case, which it does tend to be a little cold, biased a little cold, but it is again somewhat reduced with the exceptions of some outlier points. And I don't know if you can see it, this 12.2 is like this itty bitty little dot right here. One little odd spot right there for some reason. But it is generally also a reduced amount of error in the subset compared to the full ensemble. The final one, low temperature, very similar, but they have the opposite problem, particularly in the CMIP5 ensemble. This is wonderful to see this be reduced as much as it is just in the subset selection approach that we have done here for high and low temperature and precipitation. So, then the other thing, of course, is we wanted to look at capturing the spread of the possible changes. The long and the short of this particular slide is yes, our subset approach to do that. The box plots on the back of each of these is the projected change under the high emission scenario in this case for RCP 8.5 in the CMIP5 group and the SSP 585 in the CMIP6 group being the high emission scenario. One can see the box plots in the back are from all of the models together, and the red dots are from the subset in here. So we're seeing it nicely that it actually does span the range for the most part. Obviously in this case it did not, but for the most part captures the range of spread in the entire collection of GCMs that we had to work with in this case. So great for us in that, yes, our 5-member subset did actually have, in general, lower or comparable error to the entire full ensemble, be it CMIP5 or CMIP6, and it ended up being true for all of our variables to work with. Of course, the global models are not perfect. This is where the downscaling comes into play a role in that it helps to correct many of those errors that you did see in there while incorporating a lot of the local effects that help to cause some of those errors to begin with. Well, they're not represented in the global model, hence it causes some of that error to begin with. Anyway, now the next step, of course, in this is the actual statistical downscaling approach. And I make a very careful delineation between approach and technique because approach incorporates things like what training data did you use, what variables were you looking at, what GCMs did you make use of, all of those kinds of things, where the technique is just the statistical equation relationship that you use itself. For the approach here, we're using the ensembles that I just mentioned, the groups of 5. The training data is what's called gridded observations. It is the DAMET version 4, which is a 1-kilometer resolution data set for the continental United States. So for our purposes, it's important to note that the downscaling as a result will have whatever the output resolution, will have an output resolution that is the same as the training data. So it comes out at a 1-kilometer resolution. The method we used is equidistant quantum mapping, which we'll get into that a little bit more in a moment, for producing downscaled simulations of daily high temperature, low temperature, and daily total rainfall. Now, I have this table up here because we're in different generations. Of course, we have different historical simulations and future simulation periods between the generations of global models, and so that is a hurdle to have to deal with. So the historical period used in both of these for training and validation approach in here is actually a little bit different between them, but that is per the limitations of DAMET, which started observations in 1980, and the historical period simulations of CMIP5 and CMIP6, which ended at slightly different times. And so it's the same thing as we go into a future period, a little bit different future periods to work with in the output. And finally, of course, the scenarios here are a little bit different because we're in different generations of global models and different generations of scenarios here to work with. So, first thing though, why did we use DAMET? I did want to bring this up because there actually are a lot of gridded observation data sets that one could use. And that's actually because it does really perform well compared to local observations in this region. The San Antonio International Airport being used as a good example in this case to work with. Picking the grid cell with the center point that's nearest to San Antonio Airport, we're going to do a little bit of comparative analysis between the DAMET and the weather station data for the period of 1980 to when we did this analysis, we started working in 2022, so the graphics use the data from up to 2021, let's put it that way. So, what we found in looking at the data versus the weather station data in these PDF curves is that it is actually wonderfully capable of capturing the local observations from the weather station. So these gridded observations are great. We do have a slightly lower slightly underestimate of the low temperature, but we think we know the reason for that looking at the literature, so we'll get into that momentarily. But overall, I'm really pleased with how well the data captures the local things from weather stations here in the region. DataNet does compare quite favorably, though its low temperatures are a little bit colder. And we do think this has to do with a couple of different things. One of them being the fact that right here in the blue is actually where the San Antonio station is. Here where you can see the airport runway along the crest and everything here surrounding. This thing in yellow here is actually the DataNet grid box, and so the center of the cell being right here next to the thing here. The DataNet, of course, being an interpolation of weather stations, it does bring in things from a little bit more rural environment, so that in part does make it a little bit cooler because of that. But also the San Antonio station being surrounded by as much of the city as it is, we do suspect it's had some impacts from the urban heat island effect on the weather station, which does have an influence a lot on low temperatures in the area. So there is that, and why we ended up using data. Now, for the actual statistical downscaling itself, we chose to use what's called the equidistant quantile mapping method, or EDQM, as we'll talk about. And one of the reasons we used it is that it's actually straightforward and widely used. It's been well evaluated for situations like this already, so we knew it had some good use. And we actually had previously used it for the Cass region, so we do know it does perform generally very well in the Cass region itself. So we have a lot of confidence using it for this. The other reason is because in more complicated statistical downscaling techniques, it's actually often used as a component for that. So there's nothing necessarily to be gained by going to a more complicated technique for that reason. It also has a handy variant for it. Precipitation in particular, which is referred to as the equiratio quantile mapping method, is actually, for all practical purposes, it's the same technique. It's just a matter of whether or not it's an additive change or a multiplicative change. So, now for the first dose, well, not the first dose, but the second dose of equations today. How the equidistant quantile mapping works is the first thing up for every model point x here. We're looking at the cumulative distribution function to determine the non-exceedance probability tau for that particular variable, right? And that goes from 0 to 1. Based upon that, we can then say something about what is the change factor at that quantile we're just looking at. So we can take the future value from the GCM, which we know the quantile for it, and look using the inverse cumulative distribution function of the model's historical period for the same quantile from the future period, and get for ourselves a change factor at each quantile. From that, we look for the historical value that also matches that future quantile. So we're taking our future non-exceedance probability with the inverse cumulative distribution function of the observations to get a sense of what that observed value would look like. And the final step, done for every single quantile that we can, is the actual downscaled value itself, is the value here, plus the change factor for that particular quantile to give us an estimate of what that future value would look like in all of this. So that is the EDQM method in a nutshell, and of course for those of you who are more interested in knowing some of the details, that I can actually point you to all the collection of papers on that front if you're interested. As I said, the equiratio version is pretty much exactly the same version. It's just a question of what you swap out where. So in the EDQM version, it's an additive when we're talking about the change factor. But in the equiratio version, this becomes a multiplicative, a ratio for that. And the idea, of course, is precipitation is bounded by 0, and having negative precipitation values, of course, is physically impossible and unrealistic. So using a multiplicative approach allows us to avoid that problem. And in the same vein here, rather than looking doing an additive here, it's a multiplicative with the change factor also. As I mentioned, the equal ratio version, or the ERQM, is used with precipitation to avoid negative values, and this actually is a great example from the Wang and Chen paper to explain exactly why that is. The blue curve here is a model historical period, the red is a future period, and of course the black is observations, but these arrows are after EDQM is applied, where does the distribution end up? So if we're doing this with precipitation, obviously the EDQM method in this example gives us negative values, which is physically impossible to do. So on the other hand, an equal ratio approach eliminates that particular problem and does apply that change so that we can actually stay with positive precipitation. The other notes about this kind of thing and how we applied it to note here is that we did apply it with a monthly 2-week overlap, which is to say, for example, when we're doing an EDQM relationship in July, it's using all of the Julys plus 2 weeks on either side to work with to help us capture seasonal cycles appropriately as much as we can. And also the ERQM itself is not applied that way, it is applied seasonally, so looking at December, January, February, for example. The reason for this is the ERQM does need enough to have a robust sample size, particularly non-zero values. So particularly in an arid region with the western part of the Edwards Aquifer region, which is very arid, doing it seasonally as opposed to monthly allows us to have enough non-zero values to make a robust relationship. So that's all the how the heck did we do this. Now for the actual projections themselves. The projection data we have provided to the Edwards Aquifer Authority at this point, and the actual data files run through 2100, but depending upon which one you're using, CMIP 5 or CMIP 6, the future period may start at a little bit different time. What I am going to focus on here is the mid-century period, with the projected changes being defined as 2036 to 2065, and the end of century period being defined as 2070 to 2099, and looking at projected changes there. We're looking at the downscaled CMIP 5 and CMIP 6, so I will offer some comparisons to what the raw data actually looks like also, particularly with regard to looking at the historical skill, as well as the future projections in here. So there's a lot to talk about. So with the historical skill with this, so on the right-hand side is the graphic of error for the mean of the 5 models that we were working with. The CMIP 5 is on the left-hand side, the CMIP 6 is on the right-hand side, with the downscaled here being represented by EDQM. We'll just use EDQM to refer to the downscaled most of the time, so in there, but this is all precipitation on the top and temperature on the bottom in here. So, and what you can see with this is average error in here, in that the EDQM does dramatically improve the skill of the GCM for both precipitation and temperature across the Edwards Aquifer region. This is actually the raw error interpolated in here for the region from each of those 5 models in there. So dramatic improvements, which is what we like to see. It is something that is expected with the statistical downscaling. This also does hold up under cross-validation too when we run it separately. So very similar kinds of errors, if maybe just a touch larger, but very, very similar here also. So we can also look at this with respect to the different models individually. So that's what this is about, in that this is one of the CMIP 5 models and one of the CMIP 6 models, just to give you a sense of what happened with the individual kinds of models and the range of issues they had to deal with. In temperature here, this was obviously a very cold model in its original estimate over the region, and was very much improved by the use of the EDQM method. Likewise, for the case model here from the CMIP 6 group, it was also very dramatically improved here. So it's pleasing to see that one. That is one of the points of statistical downscaling, is to help correct any errors that exist in the local models. So likewise for precipitation, which is much more interesting to work with. I don't know what was going on here. I think that model thought there was a monster in here in Edwards, which I don't know, maybe y'all want that right now. But that kind of situation here was very much corrected when you got into got into that. Again, this all held up under cross-validation too at the same time, not just using the base period. So it was really, really impressive to see the results of that. So with that in mind, now it's time to jump to the other extreme with the projected changes for the Edwards Aquifer region. Here, of course, you'll see the Edwards Aquifer itself overlaid, the boundaries overlaid on these images. But for CMIP 5 on the left-hand side, CMIP 6 on the right-hand side, this is projected changes in high temperature. Typical high temperature in a given day, how much hotter might it be in the future? Mid-century is in the top group here, the end of century is in the bottom group. And again, also put together by their sort of matching RCP and SSP with whichever scenarios we're working with. A lower scenario in these two and a higher scenario with these two, and likewise, a lower scenario here and a higher scenario here. I don't think I need to belabor the point necessarily that they're projecting an increase in temperatures for this region. I will also point out that this is from each group of 5. It is the average projected change for the region from the downscale projections in here. So one thing you will note though is that the CMIP 6 does tend to be a touch warmer in its projected changes. We're going to actually get into that more in a little bit, so I won't belabor the point here. But it is good to note. Because the output is also on a daily time series, we can start to look at projections of other things also, such as the number of days the temperature will go over 100 degrees, which pretty apt considering the way this summer has been with that. So again, what we note here is, yes, the CMIP 6 is a bit hotter in that, predicting a lot more days, or projecting, I should say, a lot more days over 100 degrees with a greater increase there. So, but in general, going anywhere from, let's add like 3 months of 100-degree temperatures to the region, but we're going to get into that a little bit more with this. So, of course, like with the skill, we can look at the individual models and see the spread of the projections in there and what uncertainty there might be. This is the big winner with it being very hot, if you will. And we're actually going to come back to that because there's a point I want to make about that particular model and some concerns therein. But it ranges pretty dramatically by the end of the century, though all of them, of course, suggest things will be getting warmer. This is likewise matched. This is just bloody. Might be a little bloody scary here with the projected changes in the number of days over 100 degrees from the same group of models and scenarios. So it's certainly some dramatic potential changes there just with temperatures by itself. Now, I will say straight away that, of course, this is just high temperatures and low and days over 100 that I'm talking about. Of course, I didn't include low temperatures in here because a lot of the projected changes in low temperature, for example, are very similar to the projected changes in high temperature. So for brevity was a bit in today, but that is certainly available also if you're interested in looking at that. But it is from these kinds of things with the daily temperatures that we can also start to look at things like spring phenology and what have you in a region, or to look at drought conditions as increases in temperatures do have a great relationship with drought by increasing evapotranspiration in an area. So this would be a pretty dramatic concern. So I think projections of an increased possible drought in the region are reasonable also from these projections of temperature. So precipitation is a little bit different, and it certainly has more, as Paul kind of alluded to at the beginning, it has more spread to it, a little bit more to deal with there. But in general, the average from our simulations do suggest that the annual precipitation totals in the region will decrease, which for the western half of Edwards, which is already pretty arid compared to the eastern half of the region, might be a bit of a concern to deal with. And again, at times CMIP 6 is drier, but I will point out that there is some pretty significant variability in that, which we'll get into a little bit here momentarily. Likewise to the temperatures, the other kinds of things that we can look at are derivative variables from precipitation. So what this is actually projected change in what's called the one-day maximum precipitation. So take your heaviest rainfall event of the year, and how much heavier might it be? And as you can tell from this CMIP6 is at times, the CMIP6 group at times is a bit more intense, but there is actually a tremendous amount of variability with this also. And we're going to get into that one in a moment, but this is not the only kind of variable. So I know when I've spoken, I think I provided to Edwards, we've looked at maps of just number of days with rain, let alone 1 day maximum rainfall. You can get into things like 5 day maximum rainfall or other kinds of related variables that might be of interest. So this is where we get into the interesting part of the situation. Looking at across just particular emissions scenarios here by the end of the century with these two different models. Again, this particularly warm model, if you will, also projects it to get much drier in here. But you do have the flip side also with some of the models projecting a little bit wetter of the future in here. So there is some significant variability in here and uncertainty to incorporate into particular decisions. At the same time, you can say the same thing with the flip sides here, where this is actually even wetter of a model. This is not just true of CMIP6. The CMIP5 models had a very similar kind of story to tell, although this was a case where one model actually flipped a little bit, depending upon the emission scenario that was used. So there's a little bit of variability to work with, but that can be addressed as it were. Likewise, this is for that 1 day maximum rainfall. And so this was a particular situation where one of the models was basically along the lines of no change in that particular feature, whereas another model might project a pretty dramatic increase of, that would be ½ an inch or more there of that particular event, which I think we were talking about infrastructure before. When you start increasing those heavy rainfall events, it can have a pretty significant impact on infrastructure decision making also. This was again true, although the CMIP5 models tended to have a little bit more on the projected increases in the very heavy rain events here. So again, a lot of variability to deal with. Now what I want to do is just really quickly walk through a comparison of CMIP6 to CMIP5. And why are we doing this? Because at the same time as a lot of things are comparable between them, like they both show warming or what have you, they are different generations of global models. And while the emission scenarios are somewhat comparable, they aren't exactly the same to each other. So it is a point to walk through and just see what are the differences between generations after we've done the same downscaling technique and approach with all of them. So what this is on the left-hand side, this is temperature change, and the right-hand side is precipitation change for the middle of century and end of century, respectively, and also for in here for the different ensembles grouped by their respective emission scenarios. So you see RCP 4.5 here, and its corresponding SSP in the darker blue 2.4. 2-4.5. If they add more numbers to the emission scenarios, I'm going to be annoyed. This kind of thing. Basically, low and high. Let's go with that. With these kinds of things. So what I note with these kinds of things is, yes, there's very much a lot of overlap between the generations, which is good. Which is a good thing to see here. But we do note, of course, that particularly you can see it here in this SSP 585 is that it is projecting a warmer change in general, even though there is a lot of overlap. And in the same vein here, it is a touch drier, but again, a lot of overlap to work with. You can see this somewhat reflected also with the temperatures when you're looking at the time series of anomalies and change. Again, the red is a higher scenario, the blue is a lower scenario with temperature and precipitation on the left and right, respectively. So not all that much of a difference with precipitation, and there's a lot of variability there in that data with all of that. So why then do we have to deal with the temperature being a little bit warmer in CMIP6 versus CMIP5? So CMIP6 projected changes in precipitation are roughly similar and significant spread still applying, but the CMIP6 projected temperature changes are definitely a little bit larger, even though they have significant overlap. You get warming regardless, but why is the CMIP6 change just a little bit larger? While I have some water myself. So the big reason for this has to do with the sensitivity of the different models. One of the biggest sources of research still in climate science is determining exactly how sensitive the climate is to our external drivers to it. And this is done with a measure called equilibrium climate sensitivity. which is basically to say, if you suddenly doubled the amount of CO2 in the atmosphere and then let everything go to equilibrium again, how much warmer would the temperature be globally? And this is a measure used to, the measure of sensitivity used primarily with the models, but also with trying to understand the real climate itself, nailing down exactly how sensitive the climate is. One of the things that has been found with CMIP6 in the last year is what's known as the hot model problem, which is simply to say some of the global models are considered too sensitive, a little oversensitive, a little over hot, which is to say their model values of equilibrium climate sensitivity are a little high. This was noted by Hausfather and company in Nature last year, and then you can actually see the difference here. If the hot models are here in the global simulation versus if you remove them, what happens with that. Now, this has actually sparked a lot of conversation in the community, in the climate science community, in terms of what to do in this kind of situation. And there's actually not a fully clear path forward, which is why we hope you come talk to us if you want to use the projections, because we can work that out. They recommended in this paper that folks use models where they stick within the very likely range that the IPCC suggests is the equilibrium climate sensitivity, which is from 2 degrees Celsius to 5 degrees Celsius. So, models we selected for CMIP6, if you remember that one bloody hot model that was saying 7 degrees Celsius, well, there's the reason why. It actually does fall outside of that range, and it is considered one of the hot models. Now, coming back to the literature arguments and disagreements there that I am privy to, and you talked about going back and forth with NOAA and what have you, this is one of the reasons why, actually. I wanted to note that this is a global metric and doesn't necessarily relate very well to regional changes. And I point this out with this right here. Correlation with the average temperature change in the downscaled values to the equilibrium climate sensitivity here is 0.94. That actually relates very strongly. That is not true with precipitation. The correlation with the precipitation change to the ECS is about 0.06 with this set of models. So this is why I've, of course, still included it and still provided it. But also because this is a very hot topic. This was a preprint earlier this year, and I expect it to be published because the reviews were very favorable. It was open review process, so anybody can see the peer reviews. But this was a study that looked at the hot models and their influence in hydrology modeling. And they basically, in essence, found that removing a hot model doesn't necessarily make anything any better. And just because it is a hot climate model, a little oversensitive, doesn't mean it's a hydrologic outlier. And it can end up working just as well. In some cases, reducing uncertainty if you keep it. In some cases, actually making it larger. So this is actually very comprehensive. They looked at catchments and strivers, wow, and streams and rivers across the United States and Canada. So they do recommend continuing to use as many as possible and looking at the sensitivity with the climate models into an impact assessment related thing, groundwater hydrology, what have you, a posteriori, to see if the sensitivity of the climate model really does have a dramatic impact on the impact assessment side of things. Now, in that vein, though, of trying to make sure that range with ECS is represented, the equilibrium climate sensitivity is represented, we did decide to include an additional 2 global models that we downscaled for the region. Again, you can see no relationship between temperature and equilibrium climate sensitivity continues with respect to precipitation, and that was provided for the Edwards Aquifer region in here. So temperature change is a little lower. This is actually a little bit outside the range just on the low end, but I think it compensates quite nicely. One of the things we'll note here with this is that it does actually make for quite an improvement. So this is the same graphic as before with projected changes in temperature and precipitation with the different groups of models in CMIP5 and CMIP6. But in this case, we've added the 2 additional GACMs and removed that overhot Canyon M5, and you can actually see it does fall back very much in line with what was in CMIP5 also. So it gives us a lot of confidence as we transition. Likewise, you can say the same thing as you transition here with precipitation. It is brought a bit more in line with CMIP5 too. Though again, that's not necessarily the most important thing to go on. I will emphasize it again. It is a big conversation actually in our field right now in terms of how to handle that problem. But actually, this would be a good point to emphasize this. Later this year, I will be attending a workshop hosted by Lawrence Berkeley National Labs in California to basically examine the question and provide guidance on the use of regional climate projections in decision-relevant contexts. Now, while this is an invitation-only workshop, I did want to mention it here because I do want to go with as much knowledge and input from our potential stakeholders and current stakeholders to that group, as that will be quite a distinguished group of climate modeler experts and boundary organization representatives to try and come up with that kind of guidance for folks on how to use regional climate projections when you're dealing with problems like this, with the equilibrium of climate sensitivity and hot models and what have you. So I will make a point, because I'm going to be here all day. If you have thoughts on that, to come and let me know, because I would gladly incorporate that into my thoughts and bring that to them in Berkeley in November. Of course, you'll be able to get a hold of me at some point today or over email. So, coming to our conclusions today. Downscaling with the climate models, yes, you can provide a finer resolution in the group of GCMs and end up picking those that capture spread and historical skill at the same time. Projected changes in this Edwards Aquifer region, taking the two of them together and averaging is roughly 3 to 5 degrees Celsius increase in high temperatures in the region, with a corresponding potentially pretty intense increase in the frequency of very hot days across the region. Precipitation generally decreasing on average, but there's a lot of variability in there to work with. The final note here, as I mentioned, Edwards Aquifer does have the downscale data. I would leave it to you all on how you want to distribute it, if folks want to make use of it. We're starting on a newer project right now to produce projections, downscale projections of evapotranspiration, also with the Edwards Aquifer folks. And with that in mind, also, you probably see a bit of this afternoon, as Hakan and Devaki will end up talking about the last bullet there a little bit on groundwater and spring flow and stream flow modeling for the Edwards Aquifer, using these projections as an input. So with that in mind, we'll have my acknowledgments here. Of course, we thank the Edwards Aquifer Authority for providing some funding for this. I am also thankful this is a great project, highlighting the partnership in that while Edwards paid for my portion of the project, I will also note that the CASC itself, the USGS side, paid for another portion of the project to help with part of this. So great collaborative effort in leveraging resources there. The evaluation, the subsetting approach that you saw up there was developed in collaboration with the Regional Climate Model Evaluation System Group at NASA's Jet Propulsion Lab. Keith Dixon and his team have been my longtime collaborators at NOAA GFDL, provided some extra insight on the coding aspect with downscaling to begin with, but also I will mention again that this would not have been possible without the OU Supercomputing Center for Education and Research, who have been great partners to us in the CASC for a long time and provided supercomputing resources. And with that, I'm going to stop talking and let you all have some questions.
Thank you very much, Adrienne. That was very informative. Happy to take any questions that you might have. Yes, sir.
Thank you for the talk. It was a great talk. As we think about explanation, we all know that ENSO influences our precipitation and climate. And I'm curious, do the global climate models show changes in ENSO, and how does that affect what we're seeing here in your projections for the downscaled Edwards Aquifer?
So yeah, there are certainly projections in ENSO, projections for ENSO, projected changes in ENSO. I'm not going to remember them all off the top of my head. But some of the models do project changes in ENSO. In general, in terms of the incorporation, one of the reasons for the long time period with training and what have you is to incorporate the natural variability, which ENSO is a part of. So it gets incorporated in that way, so that ENSO is in there. We also rely on the global models to if there's an El Nino event in the global model, that gets translated by the downscaling to impact changes in the region. So changes in ENSO get incorporated that way.
Other question?
Have there been any work on looking at vegetative changes based on temperature and rainfall? Because eventually that translates to real issues with farming, ranching, even carbon capture, all kinds of things. Is there much work being done on that?
Yes. Short answer to that is yes, for sure. That I know is some of the things that has been funded by boundary organizations and their sister organizations to look at vegetation relationships with precipitation and land use, land cover changes. As how they're incorporated in the models, the global models, one of their components is a land surface model, which actually incorporates two-way feedback for changes in vegetation and the impact on precipitation and atmosphere. So in the models, it gets incorporated that way, and there's observational studies, historical studies that inform that.
Anybody else?
Any other questions?
This might be related to the El Nino question, but just thinking about these models and looking at the average changes over time and just thinking about climate variability year to year, like frequency of droughts and extreme droughts versus, flooding years. Like I could see in either of those scenarios where we're getting drier or we're getting wetter, there's still being more extreme droughts potentially happening or more extreme flooding happening as a result of it. I'm just wondering how that is evaluated.
Yeah. Sorry.
Oh, thankfully, it's not my ringtone.
Yeah.
I gave them my phone to hold on to it. My ringtone is actually a goat scream, so y'all would have had fun with that. So to answer your question, you may have to remind me just because I lost track for a minute there with that. So looking at drought, because drought is about both temperature and precipitation, there is still a lot of general consensus that even with increases in precipitation, you may still have more drought conditions occur because of the increase in temperature with the increasing evapotranspiration that's associated with that. The other thing, of course, is that one of the things that happens physically with that is that in a warmer atmosphere, it holds more moisture before you reach saturation. So oftentimes you get a double effect where you can have fewer days with rain and longer periods between rain events just because it takes so much longer to reach saturation in a warmer atmosphere. But at the same time, flooding is still a possibility because you have a lot more moisture you can rain out at the same time, which adds another layer to the drought thing because the soil in all of this is one thing that doesn't change, very much at least. And so if it's raining heavier, you have more of that runoff and not necessarily as much of it gets absorbed into the soil. So that adds another layer to the drought question. Does that answer your question or am I totally off?
So a lot of it was thinking about future and not just thinking about the mean over time, but being able to use that future to think about frequency of flooding and frequency of drought and how that's going to change year to year.
Yeah. You can look at that in a similar way because they're not meant for you to look at like one specific year in the future. They are meant for you to look at what the climate change would be in that, or the 30-year period, or more than 30-year period, that is the climate. So they're not meant to look at it that way, but one of the things you can do is basically determine from things like the standardized precipitation index or other drought-related indices, how frequently do severe drought conditions occur in the projections, and then say, okay, let's say like end of century period, what is the number of times per year on average that you end up in an extreme drought condition, let's say. And that can give you a sense of frequency of droughts. And you can do a very similar thing with flooding. Though flooding, you have to add the added component of impervious surface and land surface coverage, because precipitation can only tell you so much. If there's a lot of impervious surface, obviously you can end up with a lot more flooding situations happening. So that's a little bit of an added layer to that one. Does that? Thank you.
Any other questions?
Yeah, you just mentioned that the soil doesn't change very much, and there's a lot of people doing regenerative ag that have taken their soil infiltration, well, they've taken their soil organic matter from like 1% up to 10%, and at the same time taken their infiltration rates from less than 1 inch an hour to over 10, 15, 20, in some cases in North Dakota, 30 inches an hour, but there's examples in Texas and Oklahoma from 1 inch an hour to over 7 inches an hour. And basically you can get about 0.5% to 1% organic matter increase every year by farming in nature's image instead of fighting against her. I'm wondering if that has the opportunity to change your models if we can keep more soil moisture in the ground and increase evapotranspiration.
I think potentially so. If you can change the infiltration rate with adaptation decisions like that. Of course, when I was making my comment on the soil, it was like in absence of doing an adaptation kind of decision, you wouldn't really change the infiltration rate all that much. So yeah, I think that's distinctly a possibility, though that is not my area of expertise. It could certainly be incorporated. I think one of the things we'll talk about later, sort of highlighting Debatatia's talk, is the incorporation of the projections together with potential actions that one could take in adaptation and blending and the kinds of effects that it could have. So I think in that vein, yes, it could be added to the models to say, okay, climate change in this scenario, but what if we did this action on top of it? So I look forward to that talk later because that's going to be good too. We're all going to be good talks. It's all good talks.
Well, thank you very much. Adrienne.